Okay, calculus. We start differential equations today. This is Calc 1 differential equations, not Calc 4. But this is differential equations. A differential equation looks like this. It starts out as a derivative. Okay? We will get how to solve those. Actually, I'll just do this one. This is what's called a separable differential equation. And this is the Calc 1 type. Sometimes they are not separable, and that's where you get to the differential equations class type, or the fourth calculus class. So the first thing I want to do is separate my variables, which means I'm going to multiply both sides by dx. And I've got then dy equals y ln x dx. I've got my x's together, but I have not gotten my y's together. So I'll divide both sides by y, giving me 1 over y dy equals ln x dx. Okay. Now I can integrate both sides. Actually, I'll just write the integrals there. That was not what I wanted to do. I just want to erase this. So this becomes ln y equals, hold on. This requires a method that I don't want to take the time to do. I'm tempted to look it up. What? I don't remember what that integral is. No, I can do it faster than I can look it up at this point. UV. That's this. And then we'll learn how to deal with this tomorrow, actually. Exponential ones. You do not have to know how to integrate that in Calc 1. That's integration by parts that I just did. Okay. But does that kind of make sense? You separate the variables, you integrate both sides. What's then going to be coming is you will have to find this constant because they will give you some initial values for x and y. And then you substitute them in and find c. Okay. So, but first we need to talk about what's called a slope field. And a slope field is generated by a differential equation because dy dx represents a slope, right? And what a slope field essentially is it's taking every point on the graph, whether each point, this is 0 to 20, so I don't know how many of them they put, but basically every 2 on the x and every, oh, I don't know, 30 on the y. So at 230, what's the slope? And then you sketch in a slope. Does that make sense? So if I know This is my differential equation. I'd plug in the values for y and t and sketch the slope on my graph. In this case, I'm just plugging in the y values, so notice it's getting steeper as I go up. But because the t value doesn't affect it, it's the same for every one of these going across. Okay? You'll see somewhere it's not, where the t value is included in the differential equation or the x value. So we get a slope field. If I want to sketch a slope here, I'm going here, then looks like I get here, then it starts getting steeper as I get here. I'm going, I went a little too steep. Let's start here. That's getting a little steeper, going along the slopes. And this is theirs. Notice the lower down you start, the less steep it is. So one of the interesting things with these differential equations, they always have a plus c at the end, right? Well, that tells me a starting point essentially on a slope field. And depending on where you get a different curve that follows the slopes. Okay? In general, you have to figure out the slopes and just kind of work with them. Slope fields are a little tricky at first. They take some getting used to. This slope field, y prime is dy dx, right? This is not a separable differential equation. Oh, actually it is. That'll be separable, yeah. But we're not gonna, well, let's separate it. Let's see what happens. I'm going to times by 1 over y. So I've got 1 over y dy dx equals 2x over 1 plus x squared. And then I'd multiply both sides by dx. And then I'd integrate. When I do the integration, I only put in 1 plus c because I can just combine two different c's. Subtract c1 and c2 together, and it gets me some other unknown c. Because I don't know what it is, and I can just move equations from one side to the other. If I had a C1 on this side and a C2 on this side, I just subtract C1 from both sides. C1 and C2 are unknown, so C2 minus C1 can just be C. So that's why we only do one. Okay, with the slope field, depending on where you start, notice the slopes get steeper as I get higher on the Y. This one has an X and a Y included in getting me my slope. Okay. And yes, if I picked a point up here, it looks similar, but they are both all going down to an asymptote at 0. That was not a great sketch. But does that make sense for a slope field? Okay. You will draw a few in. They will give you a starting point. You just have to follow the slopes from there. Okay. Tomorrow we'll talk a little bit about picking slope fields from matching an equation to a slope field. And there's a few little tricks. Okay, doing a differential equation. So we have a right cylindrical tank with radius 5 and height 16 was initially full of water is being drained at a rate of 0.5 times square root of x cubic feet per minute. Find the formula for the depth of the amount of water in the tank at any time. So it's a right cylinder. The radius is always going to be full, right? The height is changing. So we've essentially got a can, and x is the height. So volume of my can is pi r squared h. H is x. If I take the derivative of both sides, I get dv dt equals 25 pi dx dt. Remember related rates? Yeah. And I have no idea why they made it negative. They made it negative because the volume is decreasing. Okay. I disagree with that statement. What I would say is dv dt is negative 0.5 square root of x. That's what they told us in the problem, so I would put the negative there. I think that makes way more sense than put the negative on the other side. I'd put it in with what they substitute for me. So I need to solve this for dt. So we're going to get the differential by itself. The differential being the dx dt. So I will divide by 25 pi. This makes sense so far? 0.5 over 25, I'm going to simplify to 1 over 50. Good so far. Separating my variables, I'm going to move the dt this way. So I'll multiply both sides by dt. Giving me negative square root of x over 50 pi dt equals dx. I need to definitely move the dx the other way, right? I'm going to take a look if the book moved the 1 over 50 pi or not. They did not. And like you could move the 50 pi as well, but you don't necessarily have to. So to move the square root of x, I got to multiply by 1 over square root of x. So that cancels these, giving me negative 1 over 50 pi dt equals x to the negative 1/2 dx. And I'm just changing that to make it easier to integrate. I will integrate both sides. I put the plus C here, so I don't need it there. Okay. Now I need to go ahead and solve. Which I know this initial condition, it's initially 16 feet high. So that means at time zero, x is 16. Plus C equals 2 times that 1/2 is square root. You looking for it here? I don't know.
Maybe I looked at the other.
I can't find my red calculator either.
Somebody take it.
Probably. Probably somebody borrowed it and just took it with them on accident.
All right.
So I'm ultimately left with this part all becomes 0. C is 2 times square root of 16, which is 8. So my equation, I'm going to take this and make it 2 square root of x. Negative 1 over 50 pi t plus 8. I will divide both sides by 2 or multiply by half. And get square root of x equals negative 1 over 100 pi t plus 4. And then I'll square both sides. If I want my original volume equation, remember this was my original volume equation? I can now plug in for x. T is not on the either. That kind of makes sense. Very convoluted. Yeah, this is not a great first example. I don't really like the examples, but I don't have better ones. Which is why I kind of did a couple of. You're not going to do the word problems off the bat. We'll grow into the word problems tomorrow. So, finding a projectile's height. Okay. We know that a heavy projectile is fired straight up from a platform 3 meters above the ground. So position of 0 is 3. The initial velocity is 160 meters per second. We know the downward acceleration is this. Or no, actually, it's just negative 9.8. So acceleration is downward, so it's negative 9.8. Keep in mind, come on. Computer's not responding very well. A is the second derivative of S, correct? So in order to do this, I'm going to multiply both sides by dt. I unfortunately cannot entirely separate this. And the notation is kind of bad. But when I multiply both sides by dt, I'm not going to cancel the 1 dt on the bottom. Come on, computer. It's probably decided it needs to update. Okay, so there we go. And now I'm just going to integrate both sides, which is this one simply becomes ds dt. The integral of the second derivative is the first derivative. Don't get caught in the notation of it. Okay? Now I'm going to take a look at this V0 equals 160 because I need to get my initial. So I need to get my plus C before I move on. And oftentimes C is this initial value, but you have to be careful it's not always. Okay. So I now have this differential equation. Okay. And we will separate the variables and integrate again. So that means I'm multiplying both sides by dt. Make sure to use parentheses there. And I get ds equals negative 9.8 t plus 160 dt. Okay. I integrate both sides. ds turns into s. Negative 9.8 becomes t squared over 2, so I divide that by 2. Plus 160t plus c. I now use my this initial equation. And my final equation becomes and this is basically your constant velocity equations from physics are entirely derived by differential equations. If you know the acceleration or constant acceleration equations, if you know the acceleration and it is a constant, we can just derive it in general and you'll get basically this. This would just be whatever the velocity initial is. This is just whatever the height initial is. And that's how they actually develop those. If this was not constant, the only way to do it is differential equations. And that's where you get calculus-based physics. Okay. But algebra-based physics only does constant velocity, and so you can do the equations. We are going to do one more example, and I'm just going to do it on the side here. So, if you look at this, I need to separate x and y. So I'm going to start by multiplying dx to both sides, giving me dy equals 2x, 1 plus y squared, e to the x squared dx. To move the y, I can't just move this y squared. I don't want to distribute, but I can move the whole set of parentheses. Does that make sense? That's a trick that's easy to forget about, as is this next piece. As I go to integrate both sides. This is the inverse tangent. This one involves u substitution. No. My u is x squared here because my du is 2x dx. Does that make sense? So what? The tangent? The derivative of the inverse tangent is 1 plus 1 over x squared of x is 1 plus 1 over x squared.
Oh.
That's on my derivative sheet. And I would have been completely stuck and stumped, except that I knew that.
Okay.
And it shows up a lot. That's a really popular one in AP. Like it's on the AP test like every other year. So the u substitution, I saw the 2x, so I knew x squared. And I was going to do e to the x squared, but I'm like, wait, that's whole derivative isn't there. The x squared part is. So this is, but simply, these two parts are my du, right? So I really just have e to the u, whose antiderivative is e to the u plus c. Okay? Or e to the x squared plus c. They did not give me any initial conditions to solve for on this one, so my c is just going to stay in there. I do need to get it to y instead of inverse tangent of y, so I'm going to take the tangent of both sides. And my lovely answer is y equals tangent of e to the x squared plus c. That's great, yeah. This is where calculus got hard again. You had a little bit of a reprieve, now it's hard again. Okay. Does that kind of make sense? You will start off with easier ones than this.
Yeah.
It's like you're gonna have to do separate the variables, integrate both sides, solve for C.
We quiz on this on Thursday.
This is not on your quiz.
Okay. Is it on the test next
Next
Thursday?
week, yes.
Oh, okay.
Tomorrow we do more of this. Okay. With ones that end up as exponentials, they're not actually any harder.
So then what's the quiz on? Is it just antiderivatives?
Hold on. Let me pause this or stop this.